welcome along to anyone who's joining us as we speak. I think the attendees are starting to be admitted into the webinar. So hello to you, thanks for coming along. This is the fourth edition of our series of online tutorials being delivered by Dr. Sherif Abbas. And as you can see on your screen, the topic today is advanced topics in VASP. So Sherif's just told me that this presentation is a little bit lighter on slides and a bit more hands-on. So hopefully we'll be able to really see him get to grips with some of the things that he's talking about. So when you're ready, Sherif, I'll encourage you to start taking us through what you'd like to talk about today, please.
Yeah, sure. Hi, everyone. Thanks for the intro, Jan. So that's the fourth session on DFT, and I'll be focusing here on a few topics in using VASP. It's mainly hands-on. Primarily have to employ van der Waals interactions in VASP, and the workflow of doing a gas absorption calculation in VASP, combination of VASP and Python. And I'll be referring to tutorial number 2, where I showed you how you can construct a platinum surface and absorb a hydrogen atom on a platinum surface using Python. So yeah, that will be also related. Just move on to the next slide. Yeah, so advanced topics in VASP. I understand that calling it advanced topics, depending on your level of expertise and your background, might have different meanings. Some people would think advanced topics might mean that it's GW, Bessel-Peter equation sort of stuff, or hybrid exchange, or well, I mean, I'm talking here in relation to the tutorials that we've been giving. So it's just advanced with respect to the third tutorial. The third tutorial was just the very basics. So this is just one level above the very basics. So I'm not going to go into the tough details. It's just a few details here that would be useful for your calculations in 2D materials and also in gas absorption. So I want to discuss van der Waals in VASP and gas surface interaction. My plan was to go over vaskit, but that will take a lot of time. So I'm afraid I'm going to have to skip vaskit for this tutorial and maybe move it over to another tutorial where I discuss how you can calculate the band structure for a defect in diamond, for example, like the NV diamond defect. I'll skip this part for this tutorial, and I would be happy to hear from you guys if you're interested in going in over a defect tutorial on diamond, for example, and then we can schedule a tutorial for that. But for now, I'll just go into details of van der Waals and a gas surface interaction. Okay, so for vaskit, I'll just quickly show you what vaskit is. It's so easy to install. And when you run vaskit, just in the command line, you run the executable for vaskit, and then you get this menu, and then you can then use these numbers here. These are all codes for functionalities in vaskit. So you can enter those numbers, and then this will let you start the functionality. So vaskit assists you in plotting the density of states, for example, for your VASP calculation. It's vaskit, so it's for VASP, for post-processing your VASP outputs. And it can also calculate for you the charge and spin density, potential, the potential function, plots the potential function along the z-axis, for example. All of these are features covered by vaskit. But for now, as I said, I'm just showing you, it's like an ad. It's an open source code. It's really, really easy to install. And as you can see here, it covers a range of applications. I would go more in detail in using vaskit when I discuss defects in a tutorial in the future, if we happen to schedule one. But for now, I want to discuss van der Waals. And you might think, why would I need van der Waals anyway? Van der Waals interaction is quite important, specifically when the weak interaction in a material is the only cohesion force. You can think of many materials and, for example, a metal like copper or iron, or silicon as a semiconductor, or diamond. And the force that holds all of these atoms are either metallic, if it's a copper, or if it could be a covalent bond, like in diamond. So that it's mainly electron sharing interactions. There is the in the spectrum of interactions, we've got the covalent, the metallic, covalent, and ionic, and then the weakest sort of interaction is the van der Waals. The van der Waals is an interaction that happens between two materials. It doesn't involve electron sharing, but it involves interaction between the polarization of the two, or the polarizability of the two materials. Those two materials could be just atoms, particularly noble atoms, which do not engage in covalent interactions, but they would engage in van der Waals interactions. Or between two benzene molecules. If you have two benzene molecules next to each other, they won't do covalent interaction because they're already satisfied with all the covalent bonding they have already engaged in within the molecule. But they would engage in a van der Waals interaction, and that interaction might either make them sit in parallel to each other, or maybe as a T structure, like that's one benzene and that's the other one. So that's the van der Waals interaction. And the van der Waals interaction proves to be extremely important to describe why graphite doesn't just fall apart into graphene sheets. And that's because each of those graphene sheets is bonded to each other graphene sheet in graphite, forming layers of graphene, each bonded to each one bonded to the other one via the van der Waals interaction. The van der Waals interaction, there are so many in the literature, so many correlation potentials or potentials that have been introduced to account for the van der Waals interaction, such as, for example, the few earliest ones by the Grimm group, and it's a very well-known one, the D2, which is supported by so many DFT packages. D3 as well, which is extremely popular. So you can switch on van der Waals in VASP by using the IVDW. By default, it's 0 until you set it to one of those numbers. IVDW equals 1, or 10 switches off, switches on the DFT2. That's the D2 Grimm method. 11 switches off the D3, which is extremely popular, available starting from VASP 5.3.4, and has been tested across a very large number of materials and molecules, mainly molecules. There's also the Beck-Johnson damping, which is 12 instead of 11, and D4, which is very recent, only available starting from 6.2, and was recently, I think last year or the year before, introduced by the Grimm group as well as a subsequent interaction after the D3 method. The Tichenko-Scheffler methods, that's the IVDW equals 2, and then the MBD, many body dispersion, 202, and then the DSC, which is IVDW equals 4. So these are let's say, the core IVDW methods, or the van der Waals methods in VASP. However, this list doesn't include two of the really cool and the recently introduced ones. There is a scan van der Waals interaction, which was introduced by the Pedro group. There isn't much, help available online as to what tags do I need in my in-car file in order to switch on scan. So what I did was I just placed it here. So you can just go ahead and take those 4 lines. If you put these 4 lines in your in-car, then you get the scan plus RV V10 van der Waals interaction in your VASP calculation. These 4 lines here. Scan is a meta GGA exchange functional, and then it uses you have to set the use VDW equals true. It sets a very particular van der Waals correction, which is not by default covered by, it's not one of those. It's called the VV, Van Voorhis interaction, and a special version of it, which has been optimized along with the MetaGGA scan and has been shown to be extremely accurate. So that's the state of the art, extremely accurate van der Waals interaction that covers not only 2D materials, but 2D materials, metals, semiconductors, molecules, a large range of systems. It has been introduced in a Physical Review X paper. Now it's very, very highly cited. You can just look up scan by going VDW space scan in Google search, and you'll find a lot of references to scan. Scan is great. It takes a bit of time to finish a scan calculation. So there has been a very highly accurate van der Waals interaction introduced by my colleague here in Brisbane, Tim Gold. He called it the FI correction method, and you can switch it on by going 263 in VASP. And now the cool thing about this one is that it competes for 2D materials. It competes with the accuracy of scan, but it's more efficient, so it's actually much quicker. And I've studied, you know, how the FI method is, how competitive it is, you know, in terms of accuracy compared to the other van der Waals methods available in VASP. I studied that in a paper with Tim, and we found that when you apply a van der Waals interaction for a 2D material in particular, one of the problems in 2D materials and van der Waals interaction is that the earlier van der Waals interactions that were supported in VASP and in general, you know, other DFT software were not benchmarked based on 2D materials. They have been benchmarked or constructed based on molecules and atoms. So when people started using like IVDW equals 11, like the D3 or the D2, when people started using those for 2D materials, they were not accurate at all. And people started to consider different things, you know, different modifications for them in order to make them more accurate. And that's why scan was invented, because people wanted an accurate van der Waals interaction method that works across the materials with different dimensionalities, not only zero-dimensional like molecules and atoms, but also 2D materials. And so that scan is pretty accurate. The FI method, which here in this plot was also introduced for the same reason, also benchmarked against 2D materials in addition to molecules and atoms. But when we apply a van der Waals interaction to like a 2D material, let's say a bulk graphite, for example, so you have graphene, or HBN, so HBN. Van der Waals interaction generally, what they do is either they would give you the cohesive energy between the layers, so the energy quantity. Either the energy quantity is going to be accurate, but the distance is inaccurate, or vice versa. So it's either that the distance is okay, but the energy, the holding energy, the cohesive energy is not okay, or the distance is not okay, but the cohesive energy is okay. You know, that has been a conundrum. Now it's people have been searching for a method that can achieve accuracy in both the energy and the distance, the length and the energy quantity. Now look at this plot here in this paper. Along the y-axis, that is the mean absolute error for determining the binding energy, the cohesive energy between the layers, so the energy quantity. And that's the mean absolute error for determining the distance, the interlayer distance, right? And for example, using Dion, the Dion method in VASP is pretty accurate for determining the energy, but very bad for determining the distance. The Tichenko-Scheffler is pretty good with the distance, but very bad with the energy. We need the errors to be zero, right? As close to zero as possible. The best one is obviously scan. So the scan RVV10 here, you can see here, is the least in terms of the errors in both along both directions. Sorry, and then the FIA is the nearest one in terms of achieving accuracy in both as well. So we can achieve an accuracy that's close to the scan if we apply the FI method, but it's 4 times less time consuming. So if you apply for the same system, if you apply a scan and the FI method, the scan is going to take 4 times more, 4 times more time than the time that the FI method is going to take. So yeah, but of course, the race towards the superior DFT methods, whether it's van der Waals or exchange correlation, continues. I'm not saying here that scan will always be the best or the FIA will always be the best, but at this stage, they are pretty good. Okay, so and I showed you how you can. We're going to make these slides available as well, and I'm going to show you. I showed you how you can start or initiate using scan and FIA in your in-car file. Okay. Next thing is, in this tutorial, I'm going to show you a workflow of doing a gas absorption calculation using VASP. Now, what the key thing I wanted to show you here is you can use both VASP and Python using the ASE package that I demonstrated in the tutorial number 2. You can use both together to make your VASP calculation much quicker. And how to do that? Let me actually show you code that I wrote for this tutorial in order to calculate the adsorption of a hydrogen atom to the platinum 111 surface. So I'll share my screen. Give me a second. I'll just be sharing a different screen. Okay. Yep, so that's the code that I wrote to do this these calculations. So the first step is you want to construct a platinum 111 surface, right? To do that, you can either use some software to cleave a 111 surface or slab of platinum, or you can use ASE. So that's exactly the code that we wrote in the tutorial number 2. We're using it here again, but this time, instead of writing a CIF file, in the second tutorial, we didn't really need to write any files, but now this calculation here, or this code, is going to write some file, and that file is a postcar. We will be using that in VASP. And then we will do calculations in VASP, and then we will bring another postcar to the ASE or to Python, and then we will be doing other calculations in Python, or basically use that postcard to build another system, and then we take it back to VASP. So let me show you how this is going to work. So the first step is we create a slab, FCC111. It's a function that's already available in ASE. Platinum atoms, size is 113, so the 1 unit cell laterally, and then 3 layers of platinum atoms. Exactly like we did in the second tutorial. We add a vacuum of 10 angstroms to the surface, and that vacuum is along the axis number 2, which is the z-axis. Now we want to find, let me just do this here. So I'll just start the terminal. Any questions, just don't hesitate to ask a question in the chat. Okay, so I just copy pasted these lines of code here. Okay, now when I type slab get positions, that's because I want to freeze the bottom atoms. And just for the simplicity's sake, we have only 3 platinum atoms here, so I'm going to freeze the bottom 2 and let the top 1 free. So the platinum atoms here start from 10. Remember when I asked that vacuum of 10 angstroms are going to be added, so it adds, for if this is a slab, 10 angstroms and 10 angstroms will be added as vacuum. And then the platinum atoms, counting the platinum atoms, starts from here. This is 10, and then 1 point, and then almost 12, and then something like 14.5, right? So the first 2 atoms in this list are the bottom 2 atoms in the slab, And those are the ones I want to freeze. Remember, we want to freeze the bottom atoms, right? So to freeze, we need to use the fixed atoms class. And then indices, 0 and 1. That's the index of this atom and that atom. So we do that. And after we're done with this, so we call set constraints, and that we pass the constraint object into set constraint. And then finally, we write the postcar. You see, if I type write pt.postcar, that would be, that's going to write for me the postcar file. It already detects that they need to write in the VASP postcar format, okay, and it writes into postcar. I'm going to show you this working now. So paste, write, and then here is the written file. I'm gonna, PT postcar, here it is. It wrote for us, that's the platinum unit cell, and these are the 3 layers of atoms, and as you can see here, selective dynamics, which means that it sets the forces, the constraints on atoms, switches it on, and then reads these FFF, means this atom is going to be frozen, same for this one, and this atom is going to be free. Okay, once I'm done with this one, I'm going to take that postcard file into this folder. You see, I created 3 folders, H2, PT111, and then PT111_H. In PT111, I have provided the incar, K-points, and podcar as the podcar for platinum, and I'm waiting for the postcar for the slab. I just need to take this one here and drag into there and just rename it to postcar. That's it. So this folder is ready for calculation. So let's go into, let me just clear. So I've uploaded that file, okay, and into my supercomputer, and I'm gonna run VASP. So the files, let me just do something here. I'm gonna delete everything, and I'm gonna upload it once again. So that's platinum. These are the full 4 files now. I uploaded into platinum 111 folder. Yes, please. And then here, VASP_std. That's the name of the VASP binary. And now it's running. So it's gonna keep running, okay, until it finishes the calculation of the platinum surface. And once it's done, we're gonna turn back to it, and I'm gonna show you the outcome. Okay, so we also want, because it's the adsorption energy of the hydrogen, we calculate adsorption energy of the hydrogen the same way we did in tutorial 2. So we need the energy of the H2 molecule. And I've written also code here to calculate the structure, or to build the structure of the H2 molecule. So we start with, we use the atoms instead of FCC here to build a slab. We use atoms. Atoms builds an atomic system, or a molecule, or whatever collection of atoms. Same, which we have discussed in tutorial 2. And then write H2.postcar. So this places 2 H atoms in space in a box that is 10 by 10 by 10, and then writes H2.postcar. And that is the H2.postcar that is written. So those are 2 points in Cartesian space, each for a H atom. And once we're done with this, we place this file here, H2, there you go. And then I just change that into postcard, and then we upload that, and then we run it. As you can see here, the platinum calculation finished. So now we have the cont card for the platinum slab, and we're going to use that cont card in a second. But let me just upload the H2. So here's the H2. Boom, 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 boom. And I'm going to go into the H2 and then run that one as well. So now I'm running the geometry optimization of the H2 molecule, right? Okay, I said that I calculated the structure of the platinum slab, so I need to bring that from its folder, PT111, as a contcar file, right? And then I'll put it here in our folder. And let's see what we got. That is the contcar. What is it? That's the contcar that I calculated just for the 3-layer platinum atoms. The next thing, again, using Python, the ASE library, we're gonna put the H atom on top of the slab. Okay, very, very easily with just one line of code using ASE. Exactly the same way we did when we did tutorial number 2. So let me just rename this to this contcar. I'm gonna rename it to PT111 opt, means it's optimized, dot postcar. Okay, there is already one there, so I'm just going to delete it. I already have it here. PT111 opt postcard, that's the one I obtained after the optimization is finished. And now what I'm going to do with it, I'm going to read it. So I used to go to VASP, we did all the VASP stuff. Back from VASP, we read this file, which we obtained from the optimization, and then add adsorbate slab, which is that slab, H, and then place the H on top of the PT atom at position 0, 0, and then with a height of 1.7 above the PT atom. Okay, so what happens next is I'm just gonna copy paste that code. And once you're done with adding the adsorbate, we write that structure into PT111 opt underscore H, and that will be ready for the next calculation, which is the adsorption calculation of the H atom. So let me just do that. Okay, so I wrote that file, and once that file is ready, we just move it into this folder, PT111 _H, and that is the file that will do the adsorption calculation of the H atom. And as you can see here, that file has got 4 atoms, 3 PT atoms, and then a H atom, which is available, which is placed on top of the PT atom. Okay, so I'm going to rename this to postcar. Okay, and then we'll upload all of these here. Okay, and once we're done with this, go to that folder. Again, that's the, if you recall, the PT111 _H. We go into that folder, and then we do the calculation. VASP std. And now that calculation is going to give us the optimized structure for placing a H on the platinum slab. And once that is done, we get the total energy for absorbing a H atom on top of the platinum slab. Now, in order to get the adsorption energy, again, going back to the second tutorial, in that tutorial, we use the formula for that calculation. The total energy for the H on top of platinum, we get that number, and then we subtract from this number, 2 numbers. We subtract from that number the total energy for a platinum slab without anything, like the pristine platinum slab that we already calculated in the folder PT111, minus the total energy of a H2 molecule divided by 2. And the result is going to be a number that's close to 0.5. And because in this particular situation here, I'm only using a system that's very simplistic. So the K points, for example, that I used here, let me just walk you through the parameters. The K points for the slab is 3 by 3 by 3 by 3 by 1. And that is manifestly extremely small K-point space for a metallic system. Typically, you would want something that's much bigger, especially that's just a unit cell of platinum, right? So we want at least maybe 15 by 15 by 1 in order to model this slab unit cell. Used here 3 by 3 by 1 so that we can see here some progress in our in the calculations. Otherwise, we'll have to submit and wait for calculations to finish, which will prolong the tutorial time and keep you all waiting and keep myself waiting as well. So the first thing is we need this to be a larger number, right? In the K-point file for the for the H2 is obviously 111, and you have to keep it 111 because it's a molecule. When you're doing a DFT calculation for a molecule with VASP, your K-point file must always be something like this. The second line must be 0, third must be gamma, and the fourth must be 111. You don't want to represent as an isolated zero periodicity system, such as a molecule, by putting K-points everywhere. Because K-points represent the periodicity of a material, but the H2 is not periodic, and therefore we don't want that many K-points for it. Just one K-point is sufficient. The gamma point is sufficient for modeling H2 or any molecule in your system. Both the K-points for the platinum and also for the platinum with the H, they have to be finer K-point grids. As I said, 3 by 3 by 1 is fine. Just for this example, it has to be at least 15 by 15 by 1 in order to get converged absorption values for the H on top of platinum, and also in order to get proper physics for the platinum slab. The podcast, of course, I obtained that from the VASP folder in my supercomputer, and that's proprietary stuff that you can obtain from your own supercomputer. And the postcard, that was the one that I generated using ASE. And now quickly over the INCAR. So in the INCAR, we, as we've covered in the previous tutorial number 3, the basics of VASP. I'm using ISF equals 2 because I'm not interested in relaxing the lattice. Abrani is equal to 2 because I'm interested in geometry optimization. Potem, that will be ignored. So we can actually remove it. We don't need it. And I spin equals 2. We need to represent the spin polarization in the system. The SCF calculation is going to keep going. That's the SCF calculation we're seeing here. That's the SCF. This will keep going until the difference between the two subsequent energies, these are total energies, right? Until the difference between two subsequent energies is 10 to the power of minus 5. And that's what's meant by EDIF, 1e minus 5. And then the geometry optimizations are going to keep going until the forces are less than 10 to the power of minus 2, EDIF G. And the forces are calculated after this loop is finished. So remember that optimization, there are two loops, one smaller loop or one loop within a bigger loop. The inner loop is for the SCF, which is this one, and the outer loop, that's the force or the atomic position optimization, the outer loop, and that's where the forces are calculated. So generally the force tolerance or the EDIF G can go in the order of 10 power minus 2, like 0.01. If you're dealing with a complicated system, then maybe it's 0.02 up to 0.05 will be completely fine. If you really need high accuracy in determining your electronic properties, then you would go 0.001 if you're dealing with a unit cell, for example, of a material. And same applies for the EDIF. You might, 10 power minus 5 is good, but 10 power minus 6 is better. And again, high accuracy demanding, you might want to go 10 power minus 7, for example, if it's a unit cell. Okay, our geometry optimization is almost nearly finished. So what I'll do is I'll just go to I'll show you how I get the total energy from the outcar. So so the outcar is where the total energy is written, right? So I'm going to go in the outcar, and then I'm using VI here, right? So if I go Shift to G, this takes me to the end of the outcar file. And let's go up here. As you can see, the forces, these are the forces at the top two atoms, the platinum and the hydrogen. I mean, 0.03 is okay. These forces are neglected by VASP because we asked VASP to neglect forces or to freeze the bottom two atoms, those two platinums. But we're fine with, but this one, well, these ones are the free ones, right? Now 0.03 is okay, so I can just take that number here, and that is the total energy for a H on top of platinum system. And let me just put it here. Okay, so I'm gonna put this as PTH equals that number, right? Now I'm gonna go out, and let's go to our PT slab. Okay, and then the end of that file, we get that number. That's the total energy of the platinum slab. So that's PT equals minus 17. And then we're going to go to the H atom itself. So CdH2 out car, and that's the total energy for minus 6.7 for the hydrogen molecule, right? So H2 is equal to that. Now the adsorption energy, E adsorption, is equal to PTH, which is that number, minus PT minus H2 divided by 2. Because it's just one atom, we assume that the H2 molecule is going to be split into two H2s, into two H atoms, right? So we're interested in the energy of just one of those atoms. So we divide the molecule energy by 2, and then we EAD is, well, I think that there's a, yeah, because of all the approximations I've done, that number, of course, doesn't make any sense. The number is supposed to be close to 0.5. So in order to achieve a better number, one has to use the finer K-grid, and importantly, one approximation I've done here as well is that I have modeled 3 atoms only in our platinum slab. Actually, in typical calculations, you want to have that slab thicker, like 6 atoms or even 9 atoms deep. And then you freeze the bottom 3 or maybe the bottom 4. And then you can have improved accuracy. But the approximations I've done here in this calculation were just meant, you know, to make things simpler and quicker, as you can see here. Let me just let's have a look at where this went to. That was where it ended. Yeah, 11 iterations. Yeah. Anyway, yeah. So that's the calculations for the adsorption energy of a H atom. Again, that has been a simplified model for the platinum and for the adsorption of H on platinum, but I'm emphasizing here the workflow. So you can use Python in order to generate your systems like that, using Python, the ASE package. And as I said, I'm using only 3 atoms or 3 levels of platinum atoms. Typically we'll go 9 here, for example. And yeah, and the K points again need to be much finer. As I said, something like close to 15 by 15 by 1 in order for this calculation to be valid. Yeah, so let's just get back to this. So all of these codes and sample input files are going to be available on the GitHub channel. So the GitHub page, a link to that GitHub page is going to be available on the Excitant Science tutorial website. So yeah, that's it for today, and I hope this is going to be helpful for your VASP exercises, and I'm happy to receive your questions.
Thank you very much, Sherif. That's a really very detailed and engaging presentation, and I think I'm sure everyone learned a lot from it, and
Thanks.
looking forward to being able to share the video of this one on the website and YouTube as well.
Sure, thanks.
We don't have any questions in the chat at the moment, but I'm sure people may be typing them as we speak. So
Yeah.
let's wait for a moment and
Yeah,
see
sure.
what we get.
Sure.
Thanks. Aha. Questions are coming in now.
Yep.
So, question from Alistair. Can
Yeah.
you please show unfolding band structure for defect structure?
Beautiful. Yeah. I would do that in a separate presentation. It's second. Where's the Alistair page? Yes. I'm more than happy, Alistair, to do that. Maybe in a subsequent presentation on defects. Apologies for not covering defects in this particular presentation, but if you're interested, I'm more than happy to do this, to do the band unfolding.
Thanks very much for your question, Alistair. It sounds like there's a lot to unpack in that one.
Yeah.
Question
Okay.
from, do you want to read out Giono's question, Sherif?
Yeah, I'll do that. So thanks. It looks like VASP researchers are trying to improve its accuracy. Of course, if they are, reflect complex environment material problems as in 2D materials. Yes. Curiosity, yeah, machine learning. So machine learning progress in this field, yes. So there's an enormous amount of data sets, available for doing machine learning. We're gonna be making available our own machine learning exercises. I've published a number of machine learning based projects where I used these enormous VASP calculations available on materials projects, for example, to predict the band gap. Instead of having to go through the pain of submitting a VASP calculation and finding the best K points and the best N cut, for example, just in a few seconds, what is the band gap for these 1,000 atoms in a unit cell? Boom, you get the band gap from machine learning. And the accuracy that have been achieved in the literature so far has been really awesome. Like my colleague Alexander Isaev, his paper in Nature Communication 2017 has been able to achieve really high accuracy, R equals 0.9. The accuracy of my descriptors are in the range of 0.87. I'm trying to push it further to 0.9. And there is also descriptors called the crystal graph descriptors, which also have been able to achieve really, really high accuracy for determining the band gap again and other crystal properties. So there has been a lot of progress for determining ground state, static properties, including such as the band gap. Now, other properties, such as, for example, the vibrational phonons, I can point you to my recent work on determining or predicting the entropy. Entropy, for example, requires the calculation of the phonons of a system. And in order to be able to predict the entropy, you need to calculate the vibrational spectrum of a system. And this takes a lot of time depending on how big the system is. But the machine learning exercise I did in this direction, I was able to achieve an R squared as close to 0.9 using neural networks. So, and I'm not the only one who has achieved such high accuracy. And there has been a lot of, machine learning exercises in the literature, also for predicting properties of MOFs. MOFs, a unit cell with 500 atoms, that sort of porous materials. There has been as well a lot of work in this space for predicting absorption capacity of MOFs, for example. My own descriptors, I was able to predict some of the porosity properties, such as the absorption, to a really high accuracy. But I found in the literature people who have achieved even higher accuracy for predicting the absorption of methane gas, for example. So the race towards the making machine learning amazingly accurate as DFT, is going really, really fast. And I can't wait to see the point in time when people ditch DFT at some point. and maybe do geometry optimization using machine learning. And I mentioned before that that's a project I'm working on at the moment, and have been achieving high accuracy as well in that respect. So yeah, I hope I've covered a few bits of your question.
Great, thanks, Sherif. I think that definitely should answer the question, hopefully. And
so yeah, so
I always encourage people to follow up one-on-one if they want to learn more. I'm sure that Sherif will be available to have more in-depth discussions.
Absolutely.
So it looks like that's all the questions we have at the moment in the chat, Sherif. Should we bring proceedings to a close and just mention to everyone who's either watching live or will be catching up on the recording that we're likely to have some more tutorials coming up in the coming weeks, and the subjects will be confirmed a bit closer to the time.
Yeah, sure. I'll definitely pay attention to defects and unfolding, band unfolding in defects, because it's a tricky calculation to do, in addition to other defect calculations such as excited state calculations. Anyone here interested in knowing about how to do excited state calculations in defects, to do your photonics calculations or photoluminescence line shape calculations? We're releasing code very soon that you can use to plot the photoluminescence line shape. And we have in this code, there's a procedure to actually do some DFT calculations, some constrained DFT calculations, and you're gonna have to use our Python code in order to plot the PL line shape. So at some point in time, very in the near future, we're going to be releasing this code, and we're going to be doing a series of sessions to show people how to use that code. And that's going to be the first time, this sort of code is available on the internet.
So that sounds really exciting, Sherif. Sure. Hopefully, we'll get a lot of interest in that.
Yep.
Well, yeah, I might draw things to a close then, if that's okay. And just going to say thank you again for taking the time to join us today, and thank you, Sherif, for sharing your knowledge again.
No worries. Thanks everyone for your attention, and thanks Ian for organizing the session.
No worries. Thanks. Bye, everyone.
Bye.